be able to solve all the problems you need to in all the interviews. So first, let's see. What is a tree? A tree is an undirected graph with no cycles, and a tree has n nodes and n-1 edges. And for anyone that's new to trees, a node are these little dots here that look like little circles, and the connections between them are called the edges. So based on this definition, which one of these is not a tree? A, B, C, and then this one up here is D.
I think B is the outlier because there's a cycle.
That is correct. Nice.
Or A, C, and D.
Nice. That is true. That is correct. All right. Next, so I want to go into why are trees important? Because they're everywhere. For example, your computer's file structure. Let's say you're in the root directory and you have 3 subfolders or 3 subdirectories. You have the binaries, the user, home. And as you can see, home has 2 subdirectories, New York and Atlanta. And Atlanta has 2 subdirectories, payroll and inventory. And there's no telling how many other subdirectories are inside of there. Next, they're the building blocks to a lot more advanced data structures, such as the heap or priority queue, red-black trees, and something you guys are going to learn about very soon, which is graphs. So far, are there any questions? Let me make sure do I have the chat pulled up so I can see everything? I'm not sure. I think we're good. I'm not sure how I can see the chat though. It's on only one monitor. All right, next. All right, first we're gonna go through the basic tree types. And I'd say the most common tree you'll see in interviews is a binary tree. And in computer science, a binary tree is a tree data structure where each node has at most 2 children, usually called the left and right child. So as you can see in this example, the root node has 2 children, 7 and 5. 7 has 2 children, 2 and 6. 6 has 2 children, 5 and 11. And this node here, 5, it doesn't have 2 children, but it says at most 2 children. So it could have 1 or 0. So it still fits the criteria. Same with 9 and 4. And any node that has 0 children is considered a leaf node. So in this graph, what are all the leaf nodes in this graph? Does anybody know?
Maybe 2, 5, 11, 4.
Correct. Nice. All right. The next type of tree is a BST, a binary search tree. And it's a special type of binary tree which follows an ordering rule. The left subtree contains nodes with values less than the node's value, the parent node's value, and the right subtree contains nodes that are greater than the parent's value. All right. So as you can see here, we have the root node 8, and we have to the left of it is 3, and to the right is 10. 3 is to the left because it is less than 8, and 10 is to the right because it's greater than 8. And every subtree follows this ordering. As you can see here, all these follow the BST ordering. You might say, why? Why would I store values in a binary search tree instead of a simple array? And the answer is because it's fast. And I'm talking extremely fast. The time complexity of a binary search tree, in the best case, is going to be log n, and in the worst case, it's going to be O of n. And to give a quick example why this is true, let's say we're looking for the node 6 in this binary search tree. This tree has a total of 15 nodes. And if we want to find the value 6, we'd start at the root, and we'd look left to right, and we say, is 6 less than or greater than 11? It is less than, so we go to the left. So we've essentially cut out half of the tree. Everything on the right side of 11, we don't have to search. So we already halved all of our possibilities. And if anybody's familiar with binary search, it's essentially the same thing. And from 7, we say, is 6 less than or greater than 7? It's less than, so we go to the left, and we've cut out this whole entire right-hand subtree from 7. And from 5, we say, is 6 less than or greater than 5? It's greater than, and we find that our value is 5, and we found it. So in a tree with 15 nodes, we've only done 4 traversals, which is very, very fast. If it was stored in a normal array, we'd have to do O of n traversals, or 15 operations, which is not too good. But we always have to talk about the worst case. Let's say we have a binary tree that is not height balanced at all, and it just has right nodes or just has left nodes. We'd essentially have to do O of n operations to reach a node. So in this example, if we want to find the node 8, we'd go to the 5 and we'd see 8 is greater than 5, so we'd go right. 8 is greater than 6, we go right one more time. And 8 is greater than 7, we go right one more time. And we had to do O of n operations in a tree with n nodes, so it's no faster than an array. So make sure you remember binary search trees are only fast if they're structured properly. Is there any questions about that? No? Okay.
Is this on the assumption that this is an ordered binary tree?
When you say ordered, what do you mean?
Like everything on the left is smaller than everything on the right.
Yes. In a binary search tree, that's always the case.
Okay.
Because let's say if it wasn't ordered and it didn't follow the rules of a binary search tree and it was a regular binary tree, you wouldn't be able to get an O of n searching capability because you wouldn't know what node is where. Let's say the 7 and the 15 were swapped and you went to the left thinking it's less than and you're at 15, everything's messed up and you wouldn't be able to get to the node you're looking for. And
Okay.
I'm not sure, can I see, is anybody typing chat? I'm not sure if I can see chat because I only have one monitor. Let me 1 second. Oh, there we go. What's my chess elo? 1500. Typing. Okay, finally. That's nice. I can see chat. All right, so let's go to the next slide here. So here we go. If anybody needs to take a picture or ask any questions about this, here's everything. So searching inside of a binary search tree is log n. Insertion in a binary search tree, the best case is log n, and deletion is also log n. And let me quickly get into the insertion and deletion. Let's say we want to add a node to this binary tree. Let's say we want to add the node 1. So let's say we have the node 1, we want to add it. We'd start at the root and say 1 is less than 11, we go to the 7. 1 is less than 7, we go to the 5. 1 is less than 5, we go to the 3. And then we see that 1 is less than 3, but 3 has no left child. So we would create a new node to the left right here and plant a 5. Or plant the 1. And that would be a 1, 2, 3, 4, 5. So 5 operations in a tree with 15 nodes. That's log n. And it's the same process with deleting a node, because to search for a node, it would take log n, and then deleting it would be O of 1. And it's the same thing with worst case scenario. Let's say we have this linked list looking binary tree. It would take O of n time for search, insertion, and deletion. Frederick raised your hand. What's going on, Frederick?
Hey, just a quick question. I noticed you said the total number of operations in the insertion. So when you say the total number of operations, you mean the 4 searches that it takes to find the place for that node, and then the 5th step being the insertion, correct?
Yes.
Okay, gotcha. Thank you.
All right, no problem. In addition, wise answer to the...
Yeah, I was just iterating on your answer to the BST property. Somebody asked whether your assumptions are based on the fact that all nodes to the left of a subtree are less than the value of a parent, and which is less than the values of the nodes on the right subtree. So I was just iterating on the previous answer.
Wait, maybe I didn't. Was that a question? In addition to wise? Yes.
No, it's not a question.
No.
Yeah,
Oh,
it's
okay,
just in
okay, sorry.
addition to
Oh,
previous
okay, that makes
question.
sense. Okay, and the question from Max Charles, so is deletion O of log n or O of 1? Well, to create a new node is always constant time, but the problem is you have to find what place you want to place that node. So that's the bottleneck of the operation. So it depends how long it takes you to find the place to plant the node. So at best case, it would be log n, and in worst case, it would be O of n. Like, for example, if this tree was completely empty and we just wanted to create a single node, that would take O of 1 time because there was only one place to place it. Hopefully does that answer your question? All right, perfect. All right, so moving on to the next slide. All right, this one's actually pretty interesting. I had a lot of fun learning about this. A perfect binary tree is a special type of binary tree where all internal nodes have exactly 2 children. All leaf nodes are at the same depth or level, and the tree is completely filled at every level. So as we can see in this example, every node has exactly 2 children except leaf nodes. All leaf nodes are at the same depth, So as you can see, if we go to the leaf nodes, none of them have a higher depth than the depth of the entire tree. And in most cases, when you're asked to find the depth of a tree, it's usually 1 index or 0 index. So this would be a depth of 0. This level here would be a depth of 1. Here would be depth of 2 and 3. So a depth of 3 has 8 nodes. And a couple fun properties of perfect binary trees is that the number of nodes is 2 to the power of the height plus 1 minus 1 nodes. And trust me, when I first saw it, I thought it was a little confusing, but it's actually really simple and it's super helpful if you're in an interview and you're asked to find the number of nodes and you have the height, you wouldn't actually have to traverse the tree. So as you can see, the binary tree at each level grows exponentially. So 1, and then it goes to the next level, and there's 2 nodes. And then from 2, it goes to 4, it doubles. And from 4 to 8, it doubles again. And that happens for every single level in a perfect binary tree without fail. And you can use this to your advantage. So let's say here the height of this tree is 0, 1, 2, 3. So 2 to the 3rd power, well, the height is 3, so plus 1. So what's 2 to the 4th power? 16, and then minus 1 would be 15. And how many nodes are in this tree? 15. And we didn't even have to count. So that's, if you have the height of a perfect binary tree, you could find the number of nodes in O of 1 time. You wouldn't have to traverse the whole tree, which is pretty cool. Like, let's say this tree had 1 billion nodes. It wouldn't take you much time to figure that out. And the next cool thing is the number of leaves is equal to 2 to the power of h. So as we can see, the height of this tree is 3. So 2 to the 3rd power is 8. And what do we know? There is 8 leaf nodes. And that was pretty cool. And I think it can help you in a couple of interview problems. Next, the height. If you're ever asked, which is a popular question, to find the height of a binary tree, just remember that the height of a binary tree is the longest path from the root node to the deepest leaf node. And how you determine this is you start from the root and you go as deep as possible and you count the number of edges. And the edges are just these connections here. So as you can see, there's 1 edge from here, 2 edges here, and 3 edges to the bottom, and the height is 3. Hopefully that makes sense. Is there any questions about perfect binary trees or the formulas or anything like that?
Yeah, so I just want to make sure I get it. So if I had a perfect binary tree with 5 levels, or sorry, 5, yeah, a depth of 5, the number of nodes would be 2 to the 6 minus 1, which is, what is that, 63?
Yeah, I think it's around there, yeah. Yeah, 64 minus
Yeah.
1, 63. Yeah,
Yeah.
there'd be 63
So the
nodes.
number of leaves would be 32. Wait, no, we said
Correct.
to the
Wait,
5th?
no? Yeah, to the
Or
5th.
did we say to the, okay,
You
then
said
yeah,
to the
32.
5th.
Yeah. Okay. And then the height would just be 5.
Correct.
All right.
All right, perfect. Let's see what's next. All right, so here is a bit of active recall to make sure everyone's paying attention. So what is the answer to this question? Which tree follows the BST property? Option A, a tree where the left node are smaller and the right nodes are greater than the parent node. B, the tree where each node has at most 2 children but no ordering rule. C, the tree where all the leaves are the same level. Or D, a tree with any number of nodes per child. All right, so we got some C's, some D's, A, C. All right. How many people are in here? Nice. Nice, I'm gonna go for 1 more minute. All right, perfect. So I see a lot of A's, which is correct. And we know this because, like, let's say, as you guys remember, the binary search tree, the left is always smaller than the parent node and the right is always greater than. So that's literally the only rule for binary search trees. If you don't remember anything about BSTs, that's it. The right is greater, the left is less. And I guess the easy way to remember this is think of a number line, and let's say you have the number 0. Everything to the left of 0 is less than, and everything to the right of 0 is greater than. So hopefully that can help you remember. That's how I remember the ordering rule of BSTs. C would be perfect binary tree, right? Let's see. All the leaves are at the same level. Well, a perfect binary tree. Yes, that would be a perfect binary tree, but it wouldn't be a perfect binary search tree. All right. Any questions about binary search trees or the rules of them? All right. I think we are good. All right. Next question. What distinguishes a binary tree from a general tree? And I guess you guys can read the question, the answers, the options. Nice, nice. I see a lot of B's. It's really good. So B is the correct answer. All right. And here is the final question. Which image best represents a regular tree, non-binary? So let's just call this option A, option B, and option C. Right? Okay, it's like, so I see a lot of different answers here. I see a couple B's. I see a lot of B's, I see a lot of A's, and then some C's. Does anybody want to turn on the mic and answer the question and explain to class what their answer is and why they think that's the answer?
I think I do.
All right, go for it, Ruben.
I wanted to say A because I saw the 5 creep over to the 9 on the right because it's greater than 5, but then it went back over to what a tree is supposed to do, and it has a 4 to the left, but the 4 is also to the right of 11. So that's just wrong to me. it's it's a tree, but it's not correct in my brain. But B is just kind of everywhere. I want to say it's B.
You are correct. And why do you
Oh,
say it's B?
It's not ordered. It does have the structure of a tree. Each node, it doesn't have a uniformity in the number of children. But A does. A has at most 2 children. It's kind of everywhere, and it doesn't has. If I go to find something, I can't use the rules of a binary tree to search this tree.
All right. All right. First, I would like to go over the difference between a binary tree and a binary search tree. This example A here is a binary tree, and you were correct by being a little like I saw you sensed something was off because it's not a binary search tree. Wait, is this binary search tree? 2, 5, 9, 4. Actually, it says a binary
it's
search
not
tree.
binary search tree.
No, wait, it's not. How so?
No.
Oh yeah, left is
7
yeah.
to
When
the
left is greater.
yeah.
Yeah. My bad. I was thinking the opposite way. Yes, you're right. You're correct. This is not a binary search tree, but it is a binary tree. Example 2B. It has 3 children here, so it represents a regular tree, non-binary, because binary means 2, and it has 3 children. So I would say that would be the answer B. And did anybody else want to say anything? Or I saw a couple comments and people raising their hands.
So I more so have a question than a comment.
Okay.
My initial thought was that B was wrong because there's not like a real order to the tree with 7 being greater than 2, 5 also being greater than 2. I was thinking that somehow violated the expectations of a tree, but just moving forward, a tree, it just, as long as there's some children there and it branches off into nodes, we could consider that a tree.
Yes.
Okay. And then
And long as there's no cycles.
No cycles. There we go. Okay, I was looking for
Yes.
like the defining characteristics that would make it not a tree. Okay, thank you.
All right, no problem, no problem. And I guess a lot of you guys are mentioning the like the ordering of the tree. The ordering of the tree only really matters if it's a binary search tree. If you don't see the search part in the tree, then the ordering could be really anything. Like as you see in this first example, the 7 is to the left of 2, which should be less than in a binary search tree. But since it's not, this is a valid binary tree, not binary search. So always remember, search trees are ordered. Regular binary trees could have any order.
Got it. That makes sense. And then do I have time for one more follow-up question?
Yeah, go for it.
All right. Can you think of like a real life technical case where we would want to use these trees? I think it'll be easier to like understand the patterns and what makes it, what's not when I'm able to think about like when and where I'd want to apply this.
Honestly, I think the best place to apply this is in an interview when they ask you to use a binary tree. It's probably the most common time, I would be honest.
Got you. It's not something you face regularly. Oh, okay.
No, not usually.
Right. Okay, cool. Thank you.
All right, no problem, no problem. And I see Max Charles said, so what about trees that branch into child nodes with the same value? Like, for example, if this 2 here was a 7, that would still be a tree. It just wouldn't be a binary search tree. Like all these nodes could actually be the same. They could all be 1 million or 7 or any number you like, but it wouldn't be a binary search tree. It'd just be a regular binary tree, or a tree if it has more than 2 nodes per parent node. And I think that's good. Everyone did pretty well. Let's see. All right, so here's the fun part. We're gonna go over tree traversals, the process of visiting all nodes in a tree data structure in a specific order. And the 2 main algorithms you're going to be learning that can solve 99% of LeetCode problems or interview problems would be depth first search and breadth first search. First, we're going to go into depth first search and explain how that works, and we're going to go a little bit into depth first search. Look up Dijkstra's algorithms for GPS. Yes, the shortest path algorithm. It's very good. In general, do not care about the node values unless it's mentioned as a BST. Yeah, I'd say in general, the node values don't matter unless it's a BST, at least for searching in the tree. Unless there's some special ordering that the problem states. If not, then the order probably doesn't matter. All right, so first we're going to go into depth first search. And I think the best way is to explain what depth first search is. Depth first search is a tree or graph traversal method that explores as far possible along each branch before backtracking. It starts at the root, explores a path all the way down before moving to the next branch. So here's a little code snippet that we're going to follow along with. And this is a preorder traversal. And what preorder means is, since a binary tree has a left and a right child, what we're going to do is perform some operation, then go left, then go right. So in this example here, we start at the 1 and we print the value. So as you can see, we have 1 here. Next, we call our function recursively and we say root.left. Root.left from the 1 would be 2. Now we're at 2. And we're in a whole nother function call. So we'd print the node. So as you can see, we're here and we've traversed to 1 and 2, and they're indicated that we've seen them by them being blue. And our traversal path is 1, 2 so far. From 2, we're going to see that we can go left one more time. We'd go left again, print the value. So we have 1, 2, 4. And while we're at the 4, it's going to say print the value. We're at 1, 2, 4, and it's going to try to do DFS root.left. As you see, it's not visible here, but the left pointer from 4 is actually null. So when it gets in that function call, it's going to hit this line here, which is called the base case. And it says if root. So if the root is true, null is not true. So it'd actually skip all of this and end that call. It'd return back up to the 4. Now we would go right. That's null. It would return back up to the 4 again. And this function call is completely done. We'd recurse back up to the 2. And since we've explored all the left subtree of 2, now we have to go to the right. We go to the right. As you can see here, we print 5. So now the path is 1, 2, 4, 5. We go to the left, not valid, recurse back up. Go to the right, not valid, recurse back up. and we've explored all left and right subtrees from 5, so we'd recurse back up to the 2. 2 has explored all the left and right subtrees, we'd recurse back up to the 1, and now from the 1, the only path we haven't explored is its right subtree. So we go to the right, and all the nodes have been explored, and a pre-order traversal of this graph is 1, 2, 4, 5, 3. Hopefully that made sense. Does anybody have any questions? I'm happy to answer anything you guys got for me. Let's see. In general, all binary trees. It says so all binary search trees are binary trees, correct? And all binary trees are trees, correct? But not all binary trees are binary search trees, correct? Yes. Is this a recursive search? Yes. Depth first search is a recursive algorithm. Recursion, yeah, it could be a little tricky to wrap your head around at first, but I think as you do more problems, it does become a little bit more feasible to do. I don't know why or how, but this example actually made recursion click. Oh, I'm very happy to hear that. So it sounds like everyone's pretty good. So we're going to go on to the next part. Next, we're going to go over a depth first search in order. So as you remember, pre-order is you do the operation, you go left and you go right. In order, think of it like a sandwich. In order, which means you're in the middle. So we have left, operation, right. So the operation is right in the middle. That's how I remember in order. In order is always the middle. And I think of it like kind of like a sandwich. It's between two things. The left recursive call and the right recursive call are like the two pieces of bread. It's kind of a weird example, but it helped me remember this. All right, so in this example here, we have an in-order traversal. So we start at the root as always. But instead of printing the root, we'd go DFS node.left. So now we're at the 2. From the 2, we call DFS node.left because we haven't hit the base case and that the first call is always .left. So we go .left, and now we're at the 4th node. From the 4th node, we go DFS.left. Remember, it's not visible here, but 4 does have a .left, it's just null. If we're going to get to the null, we hit the base case here and recurse back up. And then since before we go right, we print the node's val. So this is the first time we're going right, so we print the value 4. So as you see, we have 4 in our traversal. Now we go node.right. Node.right is null, recurse back up. Now we're at the 2. I wanted to sandwich Chick-fil-A is closed on Sundays. All right, so now we're at the 2. And before we go right, remember we print the node because the operation always happens before you travel to the right subtree. So now we got 4, 2. We go to the 5. We go left, recurse back up because it's null. Print the node, go right, recurse back up. So we have 4, 2, 5 so far. 2 has explored its right and left subtrees. So now we go back up to the 1. And we print the value 1. And now we go to the right subtree. And now we're at 3. We'll go to the left. It has no left child, so we recurse back up. And before we go right, we print the node. So 1, 3. And then we go to the right-hand subtree. We go to the right of 6. It has no tree, or it has no child. Print the node, and then right. And it recurse back up. And we've visited all the nodes. It looks like one of the nodes got cut off, but the answer is supposed to be 4, 2, 5, 1, 3, 6. And that would be the in-order traversal. All right. Everyone's doing well. Does this make sense? Okay. Next is post order. If you understood pre-order and in-order, post order should be very intuitive. It's the same exact thing, but what we're doing is doing our operation after. Oh, here we go. We got a question. So in DFS, we can go left until we hit the base case return null. Yeah, we go back up, then we hit the right and go back up. What is it in DFS? Well, it depends if you're doing in order, pre-order, or post order. That would determine what we're doing. But in order, you go left first. You always go left first until we hit null, recurse back up to go right. So yeah, I would say that's true. Yes, Max Charles. A weird case example for an order, but what about arithmetic operations? If we take the first left operand, the middle operator, and the last right operand, I think he means pre-order. Yeah. Frederick, I'm not too sure. What do you mean? I'm not sure about the arithmetic operations.
Yeah.
Are you talking about
so
the binary
it's
tree
a-
with the math in it?
I was talking about doing in order depth first search with like a complex arithmetic expression. So maybe something like what I just put in the chat, barring
Okay.
the poor placement of the um parentheses. I'll go ahead and correct that. And so like parentheses would probably be a leaf. I'd have to draw the tree out, but basically I was thinking like a parentheses would be the first or the leftmost leaf, then its parent would be another parentheses. And as I'm trying to explain it, I see that it's a bit too confusing, so I'm gonna retract that question because I'm a bit lost on the case that I was trying to think of.
I know what you're talking about. I'm pretty sure you're on it though. If you did like an in-order traversal, yeah, depending on how how each, I guess each part of the arithmetic operation is in the nodes and how you traverse it, you could return that.
Right.
Yeah, I've seen the
Right.
problems on LeetCode like that. Yeah.
Yeah.
Okay. Does everyone understand post order? I feel like are we all pretty good on that? All right. No? Could you explain again? Okay. So post order, what we're gonna do is all right. Do you guys understand the pre-order and in order? Yes. So I'm gonna explain the post order again. So remember, in depth first search, we go node.left and then we go node.right. But the order of operations, determining if you're pre-order, post-order, in-order is where you do your operation. In post-order, as you know, like in a movie, they say, we'll do it in post, the after. So after you go left, after you go right, then you do your operation. So as you can see, the first recursive call is node.left. So we start off at 1. Oh, you're lost? All right. So we start off at the root always when we're traversing a tree. We go node.left because we hit this first call. So we're saying root.left. And root.left is 2. So now we're in a new call and we're at 2. Brand new function call. So now it's going to run again and it's going to say print post order root.left. But root is not 1 anymore, it's 2. So from 2, what's to the left of 2? 4. Okay, perfect. So now we're at 4. Now at 4, it's going to call root.left. The left of 4 is null. So it's going to hit this base case and return back up. So that means we're at the 4th node. And now we're going to go print post order root.right. Root.right is null. So we'll return back up. And we just went left, right. So now we're going to print the node. So we will do 4. We'll print out 4. That's why 4 is the first node in our post order traversal. Does that make sense so far? Okay, we're getting some yeses. So are we printing the values that are null? No, we would not be printing any values are null because our print statement is inside of this if condition and it says if root. So if we're at a null node, this would evaluate to false and we'd actually skip it and the function call would end because this is the only thing inside of our function call. So we go as left as far as you can, go right, go back up, repeat. Yes, that's correct. Post order, visit children first, then visit the root node. Yes.
I like that.
As you can see. Yes. Yeah, that's actually a perfect explanation. In post order, let's say we're at the 1 here. We'd explore the whole entire left subtree here. So everything 2, 4, 5. Recurse back up. We would not print the 1 because we have to go right first. explore everything on the right-hand subtree 3 and 6, and then print the 1. Hopefully that makes sense. And we're going to get on to the...
Was it missing from that last example, but like in the text
And
at the bottom.
oh, I see. Okay, and next we're going to go into breadth first search. In breadth first search, as you remember, in depth first search, we go as far down a path as possible, and then before traversing a new branch. Breadth first search is a little different. We're going to start at a node and explore by levels. So as you remember, when we want to determine the height of a tree, this is the height 0, height 1, and this would be the height 2. So we'd explore A, and then we'd go down 1 level, explore left to right, go down 1 level, explore left to right. And it's here in definition. Visit all nodes by level, starting from the root, top to bottom, and left to right at each level. Does breadth first search make sense to everybody? And how we're exploring each level one at a time? We're going to get into the code example next, but does it make sense like on a high level? So yes. Okay, perfect. So I should feel comfortable enough to go into the... All right, I see someone said kinda. It should make a little more sense when we see the code example. So here we go. Let's say we want to do a breadth first search of this tree here. So we have a function called level order traversal. If root is null, return just an empty array. That's just if, like, let's say we're doing LeetCode and they give us a node that has a tree with no nodes. That's just a little base case here. First, what we're gonna do is, how would I want to explain this? This is not an, remember that breadth first search is not an iterative solution. It's not a recursive solution. It's an iterative solution. So we're not calling the function multiple times. What we're going to do is have a queue, and I'm pretty sure everyone here was in the stacks and queues course. So if you remember how queues work, we in queue put something in the front of the list, and to dequeue put something in the back of the list to enqueue, and to dequeue you take it from the first position. So what we're going to do is start at the root node. We're going to enqueue all of its children. So 1, we'd enqueue 2 and 3. And next, we would explore 2 and 3. We go to 2, do the same thing, enqueue all of its children. In this case, they're both null, so we wouldn't enqueue them. We go to the 3, enqueue both its children, 3 and 4, or 4 and 5. And we've popped off 3 because we've explored it, and we go down to our next node in queue. And since we enqueued 4 first, we go to the 4, look at its children, they're both null, we don't add anything, and we go to 5, we don't add anything, and we've explored the whole tree. All right, so now I'm gonna go over each line in specific. So here we have our queue, and I'd say if you're solving your problems in Python, you should always use the dequeue library. It's pretty simple, and it provides a lot of all of one operations with no overhead, really. So first we append our root. So that's us having 1 inside of our queue. We're going to have a variable called cur level, and it's just going to tell us the level that we're at on in the tree. And we're going to use a while loop. We're going to say while queue. And what this just means is while the queue is not empty. Because once the queue is empty, that means there's no more children to explore, and we've explored all possible nodes. We're going to say for blank in range length of the queue. So in the first example, the queue has only 1 node, the root. We're going to pop left, so pop off the 1. So now our queue is empty. We're going to say res at cur level. Cur level is 0. Append node.val. So as you can see, we have only 1 node. So at the 0 index, we're going to have 1 value here. That's what that stands for. And our queue is empty. Next, we're going to enqueue the left child if it is not null. So we check, does 1 have a left child that is viable to add? It is, so we add 2 to the queue. We go to the right child, add 3 to the queue. And now we pop out and we add cur level plus 1 because we just explored a whole entire level. We go to the 2. All right, so the queue is going to end that 1 iteration, and it's going to restart. And remember, we just added 1, 3, and 2 to the queue. So the length of the queue is 2. We're going to append an empty array, and we're going to say for blank in range of length of the queue, which is 2. So we're going to iterate 2 times for the 2 children. And now we go node.pop left. And does anybody know, what do we pop left here? What node should that pop off?
The node at the front of the queue.
Okay. And which node is that?
The node at the 0 index.
Node 0 index.
Since we're using
Okay.
The list. For our queue.
Yeah. All right. So that would be 2. Yeah, correct. So we'd explore the 2 and we'd say res at current level. So as you can see, we have a current level of 1 because we're at the second level, but it's 0 index. So this would be a 1. And we're going to append the value. So we have a 2. Next, we're going to say if node.left is not none, append its left child to the queue. So what would happen here if we're at 2 and we try to append its dot left?
Nothing will be appended because it has no left child.
Correct. So we'd skip that. And the same thing happens to the right because there's no right child. So we'd be done with this node. Next, since our for loop goes 2 times because the length is 2, we go to the 3. We pop it off. So now our queue has 0 nodes because we popped off the 2, we popped off the 3, and 1 was popped off in the first iteration. We're going to append 3 to the current level. So the current level is 1. So as you can see here, we add 2 and 3 is inside the array for the first level. And we're going to try to in-queue its left and right child. It has left and right children, so we queue them both in, and we have 3 and 4 and 5 into our queue. Next, we do the same thing. We pop off the 4, add its children. There is none, and we add that to our array. Next, same thing with the 5. There is no children. We add that to our array, and that's how you get a level order traversal. I feel like this one's actually has a bit more moving parts than I originally thought. How does everyone feel about breadth first search? Did that make sense a little bit, a lot? Is there any parts you guys are confused at specifically that we can like get into really quickly? You gotta take some practice, definitely. It's difficult to track, yeah. When I was trying to even just track it here, it was like I noticed it would take a little bit of experience. But I recommend just going to LeetCode and doing a couple problems, and you're gonna build up that muscle memory. Learning will happen eventually. Yes, that's the right attitude. Just do more problems, and you naturally get better. The queue kind of helps. Yeah, the queue definitely helps to give you O of 1 operations. If you used a list, it would be O of N. And that is the end of our time together. Hopefully, you feel a little bit more comfortable traversing trees. You know what a tree is, the types of trees, things of this nature. And if you have any questions about anything we learned today, feel free to DM me on WhatsApp or LinkedIn, anything like that, and I'll answer your question. Or if you guys need like a private lesson on anything we learned today, you could just reach out to me. I have Discord. We could meet on Zoom, anything like that.